Good morning. We're starting, and I've said a few words before that, but nothing of consequence. We're entering into the last 2 weeks of class, followed by the final week, and I'll just quickly review that again on the calendar. So our final exam time slot is the 13th, Monday the 13th, and working backwards from that, that is the day that we'll have our last short meeting just to discuss the exam that you'll be working on, the exam/project, which is, I'll go over momentarily, is already in place, although it needs some final tweaks to get some syntax fixed. I did, we'll have today's lecture on the 29th, and then we have the 6th, which is when I expect to complete the discussion on coding, convolutional coding, and any other questions related to that in information theory, which is the very last chapter, which is a kind of a really high-level tour through those subjects. Today we'll finish off the OFDM. We'll get into the mobile radio channel, cell planning, channel modeling for mobile radio, fading, delay and Doppler spread. Then the last little topic is the Al-Amudi, brain's going to draw a blank. I was just looking at it a couple seconds ago. I'll just jump over there. Space-time coding, and this is exactly the scheme that I was working on a couple of years ago for this company. So I've actually, when I wrote these notes, I hadn't been doing space-time coding ever in practice, but I did get a chance to work on it over about 2.5 years of working on that project for telemetry systems as one application of space-time coding. So just back at the calendar for a second. I gave out or posted last week after class a final problem set, and what I did with that problem set is I combined 2 problem sets together. So this normally, in a normal setting, would have been 2, and I decided I'll just put them together because I don't think it's going to be that scary to do that together. I mean, no difference really. So I just grouped them into the 2 chapters, 9 and chapter 11. And I put notes out, and you probably read them. And the notes I also put on the top of here. I can remove problems if you think it's going tough. Most of the problems are not that hard. They're kind of like the problems you had on exam 2, which you just look up some of the basic design concepts and then do some manipulation, maybe generate a plot in Python, just do a little bit of analysis, and then you move on. If you haven't looked at them yet, or if you don't have much to say, you can just message me and say, what do you think? I think it's pretty straightforward though. But I'm not trying to torture anybody right now. I just want to cover material so you actually try something out, and that way when you're done and over with this class, you can look back and say, yeah, I did something with that at some time. I think you're the 2 most tuned in of all my students this semester, because in the other class it just seems like a panic, and I think because they have their project due today at 5 and the way I've been getting thrashed, they're like, you're torturing me, you're giving me another project, you're giving me more homework, and I've done something similar for them. I've just weaned things down a lot because I think they feel like it's just torture. But you know, my whole deal is I want people to be out of here and be able to say they did something with these topics, and not, oh, we never looked at that, we never had to do anything, I don't know anything, because that's not going to be a selling point on an interview, and I'm just trying to cover my bases the best I feel as possible. The final project will be, final project/exam will be a little bit more work, and we'll take a brief look at it shortly. Does anybody have any initial comments on what I pushed out here? Because I'm very flexible on this.
Yeah, I haven't looked yet, but
Okay.
I'll message you like tomorrow or
Yeah.
Wednesday.
And we can talk about this next Monday too. It looks like a lot of problems, but they're all pretty short little things. So just do a little bit of this, get the answer.
Okay.
There's no real simulation involved. It's the final project exam that's got more stuff in it that I want to get you on that, but I really want to put this before you work on that. I think that will come and you will get it and you'll just say, yeah, this was fun to do and I got to try some things out, you know, with the more hands-on part. So I'll back off from that. So now in this Python projects category, I have, as of this morning, actually I worked on it a couple of days ago and then have been pondering it. And then I said, no, I think it's pretty good. I've got the final exam document, and then I have an updated sample Jupyter notebook, which has got placeholders in it for every problem that you're going to work. Some of them are just analysis problems, but I still put the placeholders in the Jupyter notebook. The only thing that's missing is that some of the screenshots in the document don't reflect the new syntax changes that are in scikit-dsp -com.digitalcom. There's a couple of things that have changed in both the OFDM part of digitalcom and then the FEC, forward error correction coding module, has got a couple of changes which just are syntax. So I think you're smart enough, though, even if you were to see the old syntax, you'd say, well, this function doesn't exist. Let me just type the name dot, you know, the module name dot, and then hit tab, and you'll see this list of functions, and you'll say, oh, this one looks similar to what I was trying to type. This must be the new whatever. But I have fixed that in the notebook. So the sample notebook that's up here, I went through everything yesterday or maybe the day before. I've just been working, I'm just working on everything for all my classes except for the lab class needs some tweaks. Just trying to get everything laid down so I can just pull myself away from that finally and focus on grading it. It sounds insane, I know, but unfortunately my mind is I have to get all this stuff lined up so I can just not worry about it anymore and then worry about the grading part, which I know is ridiculous for you guys because I've held you back, but unfortunately I have been here before. It's just not the way I'd like to do it. So let's take a look at it. There's 4 problems in here. A couple of them are analysis oriented, 1 and 2, and then 3 and 4 are simulation oriented. And my boilerplate up here of exam honor code, you know, there's you two. I'm not worried about you studying and working together because your lives are fairly separate. So, but I've had more people in this class in the past, so I have to have that on there or left it on here. Like I said, the notebook is available. You'll probably want to do the analysis problems on paper, and then you'll do some modeling. For problem 1, you'll probably do modeling on that in the Jupyter, and I've actually got some of the model built already in there. 3 and 4 is definitely all in the notebook, and it's more intense. But it's all straightforward. All the code is pre-built for you. You're not doing anything like you were for the equalizer. Everything is, you're just going through experiments and testing things out. You may have to tweak things here and there, but you don't have to, you have to draw conclusions, get plots, get coded and uncoded bit error probability plots, and you look at things with OFDM as well. And we're going to finish looking at OFDM in the Jupyter notebook I have for this chapter on advanced digital comm here very quickly too. But first problem is one that I've talked about. It's it's something I found in the internet, or maybe it was a textbook. So this is a modulation scheme that you've never seen before, so you get to study this in more detail. It's called Cross 8 QAM. So it has the 8 points set in a particular array, and it means the decision boundaries are something that you have to ponder a little bit. How, when you coherently demodulate this, do you even make your decisions? It was developed for a particular application, and I haven't read what that application was for quite a few years, but it was created for some particular purpose. It was not just, it's not a textbook thing. It was used in a standard or some government or commercial application. So a number of questions relating to that problem. And then to help you along with that, at the end of this document, I actually provide some information. Those are the optimum decision boundaries for this scheme. And if you think about it, that will be the maximum distance type decision boundary. So the decisions are made at the equidistant points between signal constellation points. So the first thing that you should see when you see this, though, is you say, wait a minute. Those are diagonals, so those decision boundaries are more complicated. They're not just like for QAM, everything was rectangular, you know, x and y axes or in phase and quadrature. So these diagonals make things more complicated. So this ends up being related to what you can do. So this is, and again, because I've used this problem before and because people I've toiled over this in the past, I'm just throwing this out here. This is a pretty reasonable way of doing the decision boundaries. And you'll study this, maybe you'll think it should be something different, but one of the things that I think I have you do in the problem is actually compare, well, you can compare the optimal to the approximate one. I think that's way up here at the top. It might be in C, yeah. Implement a simulation of the true optimum receiver, which uses the minimum Euclidean distance to make the decisions. And I also want you to gray code it, but it turns out it doesn't change that much. So this is the screenshot of what's already in the notebook that generates the cross 8 QAM waveform. And we'll maybe look at that notebook next week. I'm not going to open it up today. And then I also have asked you to compare it to 8 PSK, since that's sort of the closest competitor that we've studied, right? We haven't studied any other 8-ary scheme except for 8 PSK. QAM goes from 4 to 16 to 64 to 256, right? So the only 8-ary scheme that we looked at is 8 PSK. I guess there could be 8 PAM too, but we didn't play with that. We have the equations for it though. So it's kind of a fun problem. Second problem is a spread spectrum problem, and it just simply asks you some very simple questions about this spreading code. It turns out this was the beginning, or nearly the beginning, of 802.11. This is the 802.11b standard. I think, if I'm remembering right, and since I'm much older than both of you, you probably don't remember. How did 802.11 get started? Do you remember? Have you ever read about it? It's very popular though, right? Yeah. And it's an IEEE standard. So I'm pretty sure 802.11a was actually an optical scheme. It was free space optical. You would have a transceiver on your computer, and you would have, you know, like mounted in the ceiling of a building, you'd have a dome that had laser diodes, infrared laser diodes, and that's how you would communicate. The power levels were low, so there would be no worry about eye damage. Optical communications, especially infrared could be nasty, right? Because we don't see it. If the light was very intense, it could be damaging to our vision. It had some advantages, though. People were pushing it. There was a consortium called the IRDA, Infrared Data Association, just like there's 3GPP for cellular today. IRDA was behind all of the optical stuff, including, I'm just picking this guy up because this has a little infrared laser diode on it. IRDA controls how this remote control standard works too. Does that make sense? It's cool. I mean, once you leave the university and you start working, you realize there's standards for everything, and that's for a reason. At any rate, so I think that's why B was the RF standard. This was at 2.4 gigahertz, and then, after B, then there was all the other letters that are now in use, which are the other enhancements to the RF version. And I'm not sure 802.11a has anything, but B has got a very simple Barker code for its spreading code. So you'll have to read about that. Problem 3 is a detailed simulation study with single carrier and OFDM systems. So we have different models that you'll be playing with, but in particular, the single carrier is really not much of anything. It's just sort of to lay the groundwork, and we've already done QAM. But the biggest one is, this is the OFDM model that I have implemented. And as it says here, it's implemented in Scikit DSP-Com, .digitalcom, .ofdm-tx, and OFDM-rx. So it'll be using both of those functions to generate and play with this configuration. The transmitter is on the left, the receiver is on the right. I can see some more typos that I didn't fix. This needs to be made lowercase again too, because he changed everything. But we'll continue to talk about this in the lecture from the notes momentarily, but this has QAM as its input. It can be whatever level you want. It could be just QPSK, it could be 256 QAM, and this is what we were talking about last week, where in this block diagram, these little squares with the dots of them are representing some sort of QAM, and that's a picture depicting what? QPSK, right? Just showing 4 dots. But so each of those go into the IFFT, and this was taken from a paper that I've got referenced here at the bottom of the page. I just thought it was a nice block diagram that kind of depicted things. So my code has this same setup. You get to zero pad the ends of the IFFT when you're going from frequency to time domain. You can zero pad at either end to fill some of the FFT points with inactive carriers. And then you want to take this output in the time domain and you do a parallel to serial conversion. And then you leave room for the cyclic prefix, which we're going to talk about. And then that would go on to a digital to analog converter and an analog to digital converter formally. But actually, this has to be made a waveform. So I'm going to talk about that when we go over and look in the Jupyter Notebook. It's not something you're going to be doing in the project, but it is something that has to be done. So my function, OFDM-tx, and OFDM-rx assume one sample per symbol, so there's not actually a waveform there, but in reality there has to be a waveform. And the way we create that waveform would be some form of upsampling, say upsample by 10 or 8 or something, depending upon how many samples you want to have per symbol. And then when you upsample, you stuff zeros in. That's the nature of the upsampler, right? And then you have spectral images that you have to get rid of with an interpolation filter. And then that interpolation filter would be done in DSP, and then you would finally push that out to the RF and microwave carriers for transmission. And then at the receive end, you have to do the opposite of that. You'll have to downsample it, and then you'll have to figure out parameters like carrier frequency and timing. And I'm going to show you a little example of that in the lecture notes today too. Those factors, though, do not show up in this model. But what does show up in this model, though, is the wireless channel. The simplified wireless channel, which is sampled at 1 sample per symbol, is what you'll be playing with so you can understand the impact that HC of n, you see there in the center, has on creating interference between frames in the OFDM system. And that's what the cyclic prefix is all about. And the cyclic prefix gets recovered out over here, and then it has to be removed, and then you go through the FFT to get back to the frequency domain. And now each of these bins in the FFT contain the information bits. If it was 0 padded from over here, then there'll be upper and lower points after the FFT that just won't contain any modulation. But you take all of those streams that come out of the active carriers, and then I have in the code the parallel to serial conversion, so that what comes out is one serial bit stream, or symbol stream actually. So it'll be a symbol stream that comes out. It'll be QAM symbols aggregated from all of the subcarriers. In a real system, they might be dealt with separately, but in my simple model, it's QAM in on the left and QAM symbols out on the right. What has to be added, though, is that in order to handle the wireless channel, and you'll explore this, I have hooks inside the receiver code so that you can extract pilots, and I'll talk about pilots here in a bit. And then you can estimate the channel. So estimating the channel ends up being, in this case, a one-tap equalizer, and you'll play with that too. You'll see why that is, and it's kind of cool. It's actually very cool the way it works, because that's kind of the nature of the OFDM. So when I developed this, and then I've enhanced it over the years, the idea was to kind of give you a real flavor for OFDM if you ever get in the driver's seat of having to work at the actual DMOD and mod level. And it reappeared on my mind when this company asked me to help with their project recently, this 5G project. Remember, I've talked about that. And it's for this standard within 5G called O-RAN, Open Radio Access Network. And O-RAN has this 3.3 to 4 gigahertz band that can be used to essentially, in my view, set up kind of like a Wi-Fi access to a base station for users on their cell phones or wireless devices. And it will ultimately, I mean, right now it has two different primary modes. One mode is just no antenna beamforming, where you can just get in on a single antenna element and then back down to you on the same single antenna element. But ultimately, it also has provisions for the array processing. So you can have more than one antenna element, and you can form beams towards the users that want to get their high-speed data through this O-RAN. And the O is the open part of it, so it's an open standard. But all the providers are working on this stuff. So if you want to learn about O-RAN, just go Google O-RAN and you'll find all about it. Dr. Semiari, he's very familiar with it too, or at least he knows about it. I started learning these new terms just about a month ago when I was asked to help with this project. So, and it uses OFDM. in that case. I don't know all the intricacies though, but I do have a collection of papers that I've been gathering up. So you're going to do different experiments. Here I'm just listing what's inside the functions. So this is just a list of the functions, just so that you can look at what's inside there when you're using it out of Scikit DSP.com. And we'll look at this live, so I'm not going to look at that. We'll be talking about pilots over in the lecture notes side, but besides dealing with delay spread and using the cyclic prefix for that, there's also the need to estimate the channel phase and the rotation that goes about due to the channel. So pilots are used to manage that. So we have time and frequency with our OFDM system, and where those gray boxes are is where a pilot is located. And that's the way LTE does it. A pilot just means we're putting up a carrier that has a known bit stream in it, or maybe it's just a constant, it's just 1, let's say, 1 angle 0. And then once the OFDM frame gets brought into the receiver, you know, if you go look at what's on those carriers, any deviation of that from unity and 0 degrees is going to reflect what the channel is doing at that carrier frequency. Does that sound cool?
Yeah, I guess I'm thinking, is the idea that your bandwidth is tight enough that the channel would be relatively flat? Or is this just to give you sort of a ballpark idea of what's going on?
Okay, that's a good question. It's not relatively flat. It could vary over the bandwidth. I mean, it is relatively flat, but right at this subcarrier frequency, there might be a different phase rotation and amplitude than there is 1, 2 away. So the idea of the pilots is they're dispersed enough so that you can get a picture about what's going on at the other carrier frequencies, and then you can apply the knowledge that you get using these pilots to equalize the other subcarriers.
And you're saying it would just be a static gain at each FFT?
Yeah,
Right.
I think so. I mean, the standard details all that stuff out, but
Right. That's what you mean by the one-tap equalizer, right?
yeah, one-tap equalizer is just, that's a good question too, if you didn't think about the one-tap equalizer is just going to adjust the gain, because an OFDM, I mean a QAM constellation, if it shrinks or grows, then those slices are all, where you slice the waveform gets all messed up, right? You have to gain equalize it. So you get gain equalization, and then if it's rotated, you rotate it back.
Right, you can do that for each bin, so it's kind of like implementing in FIR in the frequency domain, right?
Yeah,
That makes sense.
it's pretty cool. I mean, I say it's pretty cool because the guys that created this were definitely, you know, they were innovative without a doubt. And the whole idea of using OFDM, remember, is that the delay spread and Doppler spreading is minimal when you have narrowband carriers rather as opposed to a wideband carrier. But with spread spectrum, which is kind of the opposite extreme, then we have another technology that we haven't even had a chance to talk about, and that's the rake receiver, which takes advantage of multiple correlations on the spread spectrum waveform. And when you set up multiple correlators, multiple despreaders, you're able to then get what's called, let's see what's the right name for that. You can resolve the multipath, because the multipath is in a spread signal, so you resolve the multipath by putting a despreader at this delayed value in the channel, another despreader at another one, so the rake finger is like a rake that you rake leaves with, and each finger of the rake is another correlator at a different delay spread value in the channel. So the signals coming at you all sum together, but the rake fingers come in and decorrelate the strong multipath components and despread, and then you get the data bits off of that when you despread, and in that process you're also taking the phase and the frequency shift into account, the Doppler spreading that can be there too, and then you can put the signal back together with the rate receiver and get the processing gain, because you're resolving out the multipath with the rakes. That was the spread spectrum way of doing it. I mean, now with OFDM and with the narrowband system, then now we have the MIMO type thing where you have more than one. You still have the same multipath issues, but you have more. You might have more receive elements at the base station, so they can resolve the multipath with the additional elements. So the game that's being played is pretty much always the same. We're trying to mitigate the channel, but how it's done depends upon the scheme. So it's, again, I say it's cool because you just have to learn to read the papers and then say, well, how is this scheme working versus another one that's been created? And I think the assumption should be that no scheme it's totally heads and shoulders above any other scheme that's ever been created. Everything everybody does, they do for a reason, and they try to do it the right way. But then for different reasons in just the technology, they want to get these same properties, but they want to get at it a different way, so they might change the modulation scheme. And so I guess CDMA fell out of favor for a variety of reasons. I'm going to talk a little bit about that too, but this was the innovative things that were done with OFDM in order to manage the mobile radio channel, the pilots idea. And an obvious thing about pilots is those channels are now reducing the efficiency of, reducing your throughput, because the bits per second per hertz of bandwidth that you would get from those gray regions is now pulled away, so you're not getting quite as much throughput. Price to be paid, though.
I guess you can kind of interpolate between them to figure out the channel characteristics.
Yeah, exactly.
It looks like what you're doing is, it looks like he's flipping which ones he's using as pilots.
Yeah, and the standards are pretty complicated in how they do their pilots. This is the equalizer, though, idea right here, where there's a forgetting factor, alpha, so that every time you get a new channel or new pilot in, you'll update it, and you're still smoothing it. So that way, if the pilots are noisy, you don't just jerk up here or jerk down here. You say, what have I been seeing the past bunch of pilots? So this is, in a sense, like an adaptive equalizer. It's just a one-tap smoothing filter. So in my scheme, though, I don't have those randomly placed pilots. I just take individual carriers and put pilots on them all the time. I don't put them in, take them out, put them in, take them out, and then move around, because I was writing something really simple when I wrote this. So I just made it pretty simple, and there's just one parameter that controls how many pilots you add in. So you'll get to play with this parameter and just see if I increase the density of the pilots, the channel estimates go up, and I can obviously interpolate between pilots to get phase and amplitude that's needed at the data that's coming in the clear regions. And if you increase the number of pilots up tremendously, you do really, really good with the channel estimate, but now you're essentially only sending pilots and you're not sending any data. So, but I just wanted to put some variable in there so you could play with it, because I think that was what I was after. I did it, I did this initially for me, but then I created it for this class. I said I want to have the students get a chance to kind of get a feel for that. Long time ago, when we had the research group with Dr. Ziemer and myself, we had students studying OFDM, and they were doing their own things for their dissertation or thesis, and I didn't have any tools like this, but this was kind of like to bring it into the classroom. The students back then, they just read the papers, and they attended the conference. They wrote the conference papers, they went to the conference, and all that worked just fine too. This was just something that I thought would be nice, and he eventually added some of it into his book. So he'll be playing with that. Then the last problem is taken from the coding theory, and it's doing convolutional coding and decoding simulation, again using everything that's available in this module in Scikit-DSP-Com, the FEC, conv.py. There's also a FEC_BLOCK for block coding, which I had a student create that. It's not super well developed, but it is inside of your Scikit-DSP-Com. I was looking at that over the weekend, trying to see how I could do an example of that maybe next week, and then I realized the documentation on Read the Docs doesn't have an absolute link to the module. It does have a Jupyter Notebook example that you can go into, but at any rate, we can do rate 1/2 and rate 1/3 codes. It's been accelerated in Rust by another student of mine, but you won't be using the accelerated version unless you want to go rummage around to try to find that. It's on the internet, the Rust versions are, and they're drop-in binary file replacements for the Python code. But it's plenty okay to just run this. It doesn't run as fast as the accelerated modules do, but it was a crazy idea I had for a student that wanted to do a project. So the basic layout of this is you'll just be doing BPSK, and we won't be doing waveforms in here. It'll just be convolutionally encoding, rate 1/2, particular constraint length code, send it through an additive white Gaussian noise channel, then demodulate it. You'll use soft decision decoding. We'll learn about that. And then you'll use the Viterbi algorithm for the convolutional decoder. And the second variation on that is to explore something that was developed a long time ago but is still in use today. And sometimes I don't know what is still in use today because the commercial standards use LDPC, low density parity check codes, which are block codes, an awful lot right now. But when the speaker was here from Zeta Associates a couple weeks ago for the IEEE meeting, I asked him about this because he's a coding theory expert, and I said, you know, I have puncturing in my module, and I said, but I'm not sure how many people use that anymore. And he says, oh, it's still used. It's definitely not out the window. It just depends on the application. I think legacy government SATCOM systems still use puncturing. So you get to play with puncturing. The idea of puncturing is after you go through the effort to encode something with redundancy, extra bits stuffed in the stream, the coded bit stream, then you puncture it just to remove some of those extra bits because you want to improve the code efficiency or the code rate. So I have my software configured to allow puncturing, and then when you depuncture, you have to insert what are called erasures, and I'll try to talk more about that. So you get to play with that too. I just thought it was kind of cool to see how that is, and you know, I've walked into that before, but if you're working in commercial systems, you're probably not going to walk into this puncturing and depuncturing because people are more into using LDPC and turbo codes too. This is part of the theory of coding. You know, coding theory legacy is this stuff though, for sure. But I don't know where you're going to run into it. I just have it. And the idea though of puncturing and depuncturing, I think is kind of another interesting innovation. Did people, and these are the properties of codes and the polynomials, and we'll see more about that. So, and then some experiments are in here just to get you up and started with using the tools. Like there's an example of the coding gain that you get with the rate 1/2 code. And this is an impressive thing that we'll talk about probably next week in the lecture, that rate 1/2 just means we put in 1 bit into the encoder and then 2 bits come out. So we're doubling the bandwidth when we go with the rate 1/2 coding if we want to keep the same serial bit rate. But taking into account the shifts in the energy per bit end to end, this plot has that taken into account. So the coding gain is very impressive that you can get with just a rate 1/2 code. And a rate 1/3 means that you're doing 1 bit in and 3 bits out. So it's a more powerful code. But then the puncturing can turn the rate 1/2 code into rate 7/8 or something like that. So you can reduce the redundancy by puncturing. And then you don't get as good a performance. The curve lies somewhere in between.
So you're thinking we'll have everything we need to know to do the exam by the end of next week?
Yeah, by Monday. That's my plan. And I worked on this over the weekend or whenever, because I was working pretty much every day, including late Thursday. I did spoil my Thanksgiving a little bit by doing some work at the end of the day. I said, no, I'm not going to push this out until after this class. And then I debated it back and forth, and I said, let me just get this out there so that way I can do what I've just done. So you just have a preview of it. I will be reposting this because some of the syntax in the screenshots there is not quite accurate all the way along. But knowing that even though you haven't been worrisome like my other classes, knowing that you're still wanting to realize what lies in front of you, I decided I should try to level it out right now so you know. I mean, I did that for my other class, and they're still been working on their project. I'm sure it was just shattering them when they saw more work being thrown at them. But, I promised it from day one, and it's all unfolding. I mean,
And then I was just going to say, this looks like a long exam.
It's kind of long, but it goes pretty quickly. I mean, 3 and 4 takes some computer time, but it doesn't take a lot of work to do it. You'll have to fiddle around a little bit to understand how to drive things, but I have examples in the notebook of stuff already started. You just have to learn about turning some knobs, and I'm going to have to review that probably with you because I have to remember how all my knobs work, especially on the OFDM. The coding is pretty straightforward though. The first problem is probably the most interesting problem with that cross 8PSK from a modulation theory standpoint. So that one is kind of a fun, kind of a theory-based problem where you get a new fresh modulation scheme you haven't analyzed before, but you can leverage off of QAM and how to set up your decision regions and get your error probabilities.
On a related note, I had a question about the DFE.
Okay.
The exam. So I noticed when I ran it, I would essentially almost always get either like very close to 0-bit error or 100% bit error. And so I assume when I got 100% bit error, it basically locked into an incorrect phase.
Okay.
Like I got off, I assume, by like a pi/2 rotation.
That's possible.
Sometimes I'd get like 98% error, or I'd get like 2% error. So
Yeah, and that sounds like something that my error probability detection algorithm would do. It would sort of false lock, like you said. And
is there an easy way to tell, is there a problem with my Python code, or how your error detection is locking, or like what
well,
is
because you're using because I had you use the gray encoded and decoded PSK, it gives you serial bit streams, right? So it gives you a serial bit stream back. So if the constellation locks like this, and then it goes into that decoder, it's going to then put all that back into a serial bit stream with the rotation present, and it scrambles things up. So I think that's what you're seeing. In reality, you wouldn't do that. In reality, what you would do is you would have a preamble in the received waveform where you would know exactly what the bit pattern was, and then what you would do is you would correlate on that preamble in the receiver, and you would figure out, what do I have to do with my constellation? If it happens to be rotated, I'm going to detect that with this preamble, and then I'm going to rotate it back before I put it into the decoder.
Right. I guess I'm just a bit concerned about falling into those issues on these problems also.
There's nothing like that.
Okay. I guess
Because there's no locking mechanism, there's no adaptive behavior that I can think of. There might be something in the one-tap channel equalizer, but I don't know. There is part of the results that have been perplexing to me, and I've never really drilled down in detail. But this, I knew this could happen. As a matter of fact, when I put that rotation in there, I said I better not rotate it too far, because if it gets confused, you know, like if I rotate by 45, it's going to be right at the halfway point, and it's maybe going to spin around and find its taps to rotate the phase. And I said, oh, that'll be catastrophic if that happens.
Yeah,
and you're telling me it is.
With a smaller rotation, I basically always locked correctly.
Yeah.
And then as I approached 20 degrees, there's like some probability I'd get 100% bit error and some probability that it would lock. So
that's called, in a phase lock loop, there's a mathematical name, it's called equivocation. And I think we equivocate in our lives. It's like, do I do that or do I do that? You know, you have this equivocating thing, and that's exactly what can happen.
So anyway, I cherry picked what I sent you.
Yeah, that's fine. I did some experiments when I wrote out the solutions. I added in some error probability checking just for the fun of it, and I did notice, mostly, not consistently though, that the DFE worked a little bit better at a lower signal-to-noise ratio than the decision-directed did. And that was like at around 9 to 10 dB in that area with that amount of channel distortion. And that's kind of, I would expect that, but that's what they say happens, right? Because of the DFE, the post-cursor taps are noise-free, whereas in the decision-directed, you have the precursor, post-cursor, you know, one in the middle.
Right.
These taps over here have noise on them, so they would be jiggling around and not be able to get as good an estimate at lower SNR.
At some point with lower SNR, my filter never converged.
Yeah.
Because I suppose it kept trying to optimize, but there was too much noise. So then my constellation plots looked like complete garbage.
Yeah, I believe that too.
And it's interesting because there's a very clear delineation of when it locks versus it's in the weeds.
Yeah, and that's also the convergence parameter. Did you play with that?
A little bit, maybe.
Because if that stays too big, then it will be in a hurry to converge, but then because it's so big, it will just keep getting thrashed around by the noise, and it won't.
So maybe at lower SNR, I need a lower mu.
Yeah, exactly. Because that is actually a part of the stability theory of the least mean square algorithm. That noise factors into the stability of that feedback control system, and if it's too large, if the noise is too large, then you have too much gain due to the noise, and then that makes the feedback system unstable.
Right. So it seemed like it needed a minimum SNR, and then it performed much better.
Yeah.
The no equalization, but below that, it was far worse.
Right. Which, you know, since I'm rambling along about that and mentioned LDPC, the more modern contemporary coding schemes is we can operate closer to the Shannon limit, and we'll talk about that in chapter 7 of the notes, which means that you're going to operate at lower EB over N knots, which means some of the things we've looked at aren't going to function properly because they just don't work when the SNR gets down that low, so you have to have other things to manage that. And in the Viterbi algorithm, again, the speaker from Zeta Associates talked about using per survivor processing, where you actually do something with the fact that you're at such a low SNR that the Viterbi algorithm has to get fed. You have to take information from inside of its correlations and use that to do some sort of crude phase tracking with this per survivor technique. And he talked about it I had seen it, but I'd never really studied it. And the way he explained it in his talk was pretty interesting. It said you don't actually just have one Viterbi algorithm. Effectively, you're going to pre-process with some estimates that come out of the Viterbi to go into a phase estimator or phase control block, and you have several paths so that you can manage that at low SNR better. Because that seems to be the trend, that everybody wants to be able to operate at lower SNRs because they have these powerful LDPC codes now that they can work with. And I suppose that's true of your work, because it's such a high data rate and the signal integrity messes up the eye. So
Yeah.
they use LDPC in that. Is that true?
Well,
The
we
back
use
end?
block codes like 66, 64 and things like that.
Okay.
Yeah, which is like 2 to 3 parity. Like, yeah, you take in a block of 64 bits and then you'd usually transmit between 66 to 70 bits. So
Okay.
It's pretty low density because I think over a wire you have pretty good SNR usually.
Yeah, it's the signal. It's the signal integrity though in this.
Yeah.
That's the issue there.
But yeah, there's some, but you definitely need a lot less FEC on a wire than you do wireless.
Right. Okay, so I'm going to leave that behind and go back over to this.
I imagine, I guess, the other thing for DD is you don't know, or for our sims, we didn't know a priori the input signal, but I imagine maybe you could do a bit better if you trained on like a known input for some amount of time before being
Yeah.
directed.
And that could be, again, the preamble or a mid-amble.
Right.
And that would get it closer to the starting point. Actually, that's what the mid-amble idea is you've got, you can correlate with a known pattern, and then you can basically drive or pre-tune the equalizer to get very close to where you want it to be. So thinking back to this bowl idea, rather than it being way up on the sidewall of the bowl, it's much closer to the bottom of the bowl, and it doesn't have to drive that far down.
Yeah.
And you can use smaller mu then and just slowly come in. Well, not really slowly, but just take a few small, tiny steps and be at the bottom, and then hang out at the bottom because your step size is small. So there's actually adaptive mus too that you can put in.
And that might be better with low SNR.
Yeah, it could be then too. It's minimum mean squared error, so it's balancing intersymbol interference against the noise, and that's true always. So going back over to OFDM, now back in the chapter, we talked about the standards, and then I put this in the notes a number of years ago just to talk about how LTE was working. The downlinks that come from the base station to the handset are OFDM. The uplink is the subcarrier frequency division multiplexing. But this just lets you see the detailed blocks inside of there. I didn't really want to try to explain them, but you can see down in the lower levels, closer to the physical or waveform areas, you're seeing the IFFT and then the cyclic prefix insertion, and then finally you're going to actually modulate the carrier, you're going to upconvert it and go out to the power amplifier with filtering, making it into a waveform, and then on the opposite side you're doing the down conversion. And now, if you're wondering where I'm at, I'm pretty much right in this area. So I went from here and now I'm back over here, and removal of the cyclic prefix, and then go to the FFT. The rest of this stuff, you see equalizers in there and other things from the channel estimation, more sophisticated. MMSE we know is minimum mean squared error, and MLD I think is maximum likelihood detection, but I could have that acronym wrong. So now getting into how my scheme works, it was motivated by pictures like this. So the downlink uses OFDM, And we have the carriers that are set above and below the nominal DC carrier until it's actually moved up to a carrier. So complex baseband, it's the DC subcarrier. And you have a certain channel bandwidth, you have transmission bandwidth configuration. In my code, I can control how many of those subcarriers I'm going to turn on by turning a single switch, and that's just the way I set it up. So the transmitter puts out the QAM signals go into the serial to parallel. Each of the individual channels feed the IFFT, and again in my scheme I've got 0 padding, which is part of the FFT, so this is all together. So I've got carriers above and below that are not fed with anything, they're just filled with, they're just blank. And then cyclic prefix insertion. So what is the purpose of the cyclic prefix? I pointed this out last week. When you go through an OFDM symbol, when it goes through the channel, because it's this composite of all the subcarriers, when it goes through the mobile radio channel, will be some delay spread, and that's what that upper little figure is there. It's just saying there's a spike at 0, and then there's additional echoes due to the multipath that carry on. So when that symbol arrives at the receiver, it's got those echoes that are going past, you know, it's and filling in to the next OFDM frame. And if we don't do something about this idea of the cyclic prefix, then we have corruption. So that it's called inner symbol interference, which we've talked about before. It's the OFDM symbol in this case because it's actually in the time domain, and then it goes back to the frequency domain with the FFT at the receiver. So that inner symbol interference translates into the individual carriers in this special way. So what is done is you have a cyclic prefix that you add in to the beginning, which does reduce the efficiency of the OFDM frame, but the cyclic prefix is thrown in there so that you can handle the inner symbol interference by having this region in this picture right here. That's just saying that that's sitting in there so that it doesn't get corrupted by the inner symbol interference from the preceding frame. That cyclic prefix, though, is just a padding that's in there. It's actually just a copy in the code. It's just, you just make a copy and throw that in there. But that gets removed before you go into the FFT. So this was not my figure. This came from some book or some source just to try to explain why the cyclic prefix works. It has to be removed again, though. It's put in there just to manage the inner symbol interference before you FFT it. And I could try to justify it further, but you're going to justify it to yourself, because one of the experiments you do in problem 3 is you're going to change the length of the cyclic prefix in the code, and you're going to look at the quality, and you're going to keep increasing it. You know what the delay spread is of the channel, and I have you do an experiment where you make a cyclic prefix of length 1, 2, 3, 4, and you know theoretically it needs to be the full length of the delay spread for the channel. So you're going to look at it and just see things don't resolve or get cleared up in terms of inner symbol interference impacts until you make it long enough for the channel delay spread. So it sounds kind of crude, but I'm making you do it just so you can see how significant it is, and it is significant. This gets back to explaining how the cyclic prefix is done in LTE for a particular sampling rate, and it's just showing you the locations of the cyclic prefix that gets thrown up. In the notes, or the book I was taking this from, it's called the LTE slot structure. The uplink is because the handset has battery power and OFDM has high peak to average power ratio. We'll see that in a simulation shortly. It's called PAR, peak to average ratio. Power amplifiers need to be backed off more, which means they're more inefficient from DC to RF energy conversion. So that shortens battery life. So at least in LTE, they made the uplink, the subcarrier FDMA. So you have an FDM system where you have multiple carriers, but you don't go through the same process that's done with the official OFDM. I have not studied this in any detail. I just put the block diagrams in here just so you could see what it looks like, but I'm not prepared to explain the details of it. But it was just a variation so that you wouldn't have as much. The goal of this SC FDMA is to reduce the peak to average ratio so that the amplifiers are more efficient. Does that sound good? Longer battery life? It almost looks identical, but it's not, and I guess I haven't taken the time to go delve into it. But this is Advanced Data Communications Jupyter Notebook, which I reposted because I added below where we left off last week with direct sequence spread spectrum with jamming. I added this picture from the project just to explain how the code is working, and so I can just run this, and I'm creating QAM. So just the way the transmitter is working, well, the call to the QAM baseband is just creating a source of complex baseband symbol samples, and I don't really want the waveform. All I really want is the symbols, which are, I guess I need to look at that again. Oops, can't do that. I always forget that when I'm running my video screencaster, I can't use the keyboard commands, but let's just look at down here. I messed this up. There we go. These are just the points, constellation points of the QAM. So that's what the OFDM transmitter needs, and that's what comes out of DC.QAM. You can see the values are like 1, -1, J, and so on. So they're the constellation points for the QAM. And then what goes on inside of here, NF is the number of filled carriers, again going from the notation that I took from that paper, and NC is the total number of carriers. And then later, not right now, you get to use this to put in pilot codes. 0 says no pilots. And then here you get to decide if you're going to put in a cyclic prefix. Right now that's turned off. And then you get to set the length of the cyclic prefix. These last 3 variables is what you're doing in problem 3 of the exam. But for here, if I fill all of these up, let's say 64, I'm going to fill 64 of 64, and then in my code again, I have the DC carrier turned off, and that's just sort of a reference value that's in there. That's why that one is pulled down, but that's that carrier. I'm just doing experiments with it only half filled. And then if I go ahead and send it into the receiver after I add some noise to it, the receiver lets you set, again, the same matching parameters, how many carriers filled, how many total carriers, and then the period of the pilots, which is 0 right now. Is the cyclic prefix present? No. What's the length of the cyclic prefix? It's 0. And then for channel estimation, this is the forgetting factor in that channel estimator, and the HT is a way of putting in the known channel phase, the known channel, so you can just hardwire this as if it's a perfect equalizer. If that is set to none, then it estimates it from the pilots, and you'll play with that too. So you can always put in perfect when you have pilots, and then you can do a perfect job. But if you take it off, then it will try to estimate it from the pilots. So you'll be working with those knobs as well. So here, let's see, make sure I'm doing this correct. I guess I have cyclic prefix turned on, but my cyclic prefix length is 0, so there's, I think having this true or false doesn't matter if that's 0. I'm not sure why I had it like that, but I'm just going to use it like that. So this was 16 QAM, and it's coming back looking fine. If I was to reduce the SNR down, then you can see the dots are starting to spread because we're having noise on the individual carriers. Let me take this down to 20. And this you'll be doing in the project, but this is kind of a tricky little scaling thing. NS is the number of samples per symbol, so normally that would be, say, 5 or 10 or 8. In this case, it should be 1. But because of the fact that I'm not filling all of the carriers, I need to adjust the noise upwards so that the carriers that are active get the proper values of noise set. So I raise it up by 64/32 because inside of the complex additive white Gaussian noise, it's doing a measure of this received signal energy, and it's seeing less signal energy because not all the carriers are full. So I scale it accordingly to make sure it properly normalizes that. Otherwise, it would put in a different noise value. So that's in there. I'm just going to set that back. So now I want to do something that I've never shared with this class. It's because I'm working on this 5G project. I had to start thinking about what happens when you upsample and then filter. So I decided I'd upsample by a factor of 4 to make it a nice analog-looking-ish waveform. And I decided for my interpolation filter, this is just the upsample function, where I'm going to upsample by a factor of L, which means I put in L-10 samples. So now I'm going to get a lot of spectral images, which you're seeing down here. But because I'm throwing in an interpolation filter, I decided I would just use, because it was convenient and handy, I'd use raised cosine impulse response. And I'd kind of set it to the same alpha or beta factor and 8 samples, just to kind of shape the spectrum so that what's going on in here is my analog transmitted signal that I would shift up to a carrier frequency. These things being down, like 100 dB or close to 100 dB are just all the images that I wanted to get rid of. So it looks like an analog waveform. I intend to use this in some modeling for this project, but I'm showing you how I started down this path, because I'm in charge, or I'm responsible for DSP algorithms and things that need to be in the transmitter and the receiver. So I wanted to get my feet on the ground a little bit. So it's curious at this point, you'll see if I was to take this back up to, if I was to transmit this with the full, all the carriers active except the baseband one, and then go down into here. What does that look like? I mean, from a distance, it just looks like a raised cosine spectrum for digital modulation. you see that little dip in the middle, that's because I have the DC carrier turned off. But otherwise, you'd look at that, and if you're looking at a spectrum analyzer, is that OFDM? Is it a single carrier? I mean, it looks very similar, right? But it's not what it is. You go inside of that and you'll see it's, much different. So because I did my little experiments in here with this at 32, I'm going to switch this back. Then I'll go into here again.
So I suppose you're saying one of the points of OFDM is you can essentially choose your bandwidth efficiency by picking how many bins are carriers or not, right? So
Yeah, you can activate and deactivate. And I guess when I first learned about OFDM, they said, oh, if you know you've got a line of sight path where you've got a strong multipath that's putting a null in the frequency band, you can just elect to not turn those carriers on at all because they're going to be pretty well destroyed by the channel. And if the channel is fixed, I mean, just not put any energy in those and just work around that channel issue. So that's another part of the flexibility issue of OFDM that's available. So here what I did is, just run this cell again. I decided I wanted to see the envelope fluctuation. So I take the envelope and I'm going to find the mean of the envelope in dB by taking 20 log base 10, the absolute value, and I'm just picking time samples between 5,000 and 10,000. By the way, I didn't point out that when you go through the OFDM transmitter, the length of the one sample per symbol, I requested 10,000, but in order to fit FFT lengths and for the particular configuration of the CP, which actually isn't included in here, or any other factors, I guess I have to think about this. I'm not getting 10,000, I'm getting 9,984, but that sounds reasonable because of the way things had to be framed with the FFT bins and then the powers of 2. So just wanted to point that out. So here's the fluctuation then when I run this cell. I then plot the envelope and then I subtract the dB mean, and I'm just doing that so that I can put that red line in there at 0 to just show you that if it was a constant envelope scheme, the fluctuations would hold on that red line. Like a constant envelope scheme that we've looked at would be, the only real one is Emory PSK if we're using rectangular pulse shaping. As soon as we put in a raised cosine pulse shape, we get amplitude fluctuations. And in OFDM, this is the annoying factor, and one of them here is going up above 10 dB, but they tend to hang around 8 dB. So this is the back off required in the power amplifier, because if you don't want to distort the waveform, you have to have headroom in the amplifier, power amplifier. And this is that peak to average power ratio stuff that I was talking about, the PAR, the fact that it varies around. And this was for the particular raised cosine. Well, this is just because of the FFT and then the raised cosine shaping. So it's mostly just due to the FFT because I'm now down at, well, I'm not at baseband yet, but it's just showing you there is that peak to average. So now what I'm going to do is bring it into the receiver. I can add noise as I see fit, but now I'm going to pretend that the signal has some frequency shift in it and going from transmitter to receiver, so I don't have perfect knowledge of the carrier. Initially, I'm just going to set this to 0. I'm looking at the spectrum again, and what I'm doing here is I'm decimating the signal spectrum by 10 because that was what I oversampled by 10. And down below here, I would just take a look at the constellation plot again. I've got to carefully decimate by 10, and then these factors are timing factors. that I can or cannot use if I so choose because of what I did by creating a waveform. You don't have to deal with this in the project, but I'm just wanting you to see this. Again, this was motivated by my studying for this 5G project. So what I'm going to do is I'm going to put in a very small amount of phase rotation into this system. 1e minus 5, you don't really notice anything in the demodulated carrier, but now if I look at the scatter plot from the receiver, it looks like artwork, right? I find this intriguing. You're going to see this also in the project, but not for the same reason, but it's just precessing around because of the frequency error. I find it intriguing because it looks like art. Actually, here in the US, we had a toy that's called Spirograph. You know what I'm talking about? Yeah. Is that something you've seen before? A spirograph is a thing that has gears of different sizes, and then you can put a pencil in a hole, and then you can do. So doesn't this look like a spirograph? Okay.
Have you seen videos? There's a guy who like used the Fourier series to like make some spirographs to like draw like Homer Simpson or like arbitrary images.
No, I haven't seen that. It sounds interesting now.
I'll send it to you.
It just, I don't know. To me, it's interesting because we do things in our life when we're growing up, toys and stuff, and it's like, wow, that reminds me of that. It's just kind of interesting. So the other thing, though, is that, okay, so I set the frequency back again to 0. So we have to have the frequency error managed with a carrier phase estimate. But so now this will come back again. But if I sample just 1 or 2 samples off, and this is at a 10x oversampling factor, so this would be like 20% timing error. A timing error makes it look like a phase shift error in the constellation, and I think that if you think about that, that makes sense because of the fact that we have the FFT and IFFT in there.
Yeah.
Does that sound right?
Yeah.
Okay. So we have to have the timing right. And if I set this to 1, it will be 10%. So it's a little bit closer. I can't set it to fractional values unless I was using an interpolator, but so I thought that was interesting. I put this in here originally, but now what I would like to add, if I could add anything, is adding a channel simulator for delay spread and Doppler spread, and we're going to go start talking about that here pretty soon. I actually have that simulator that I wrote in MATLAB many, many years ago. I've just never translated it to Python. So let's go back over here. So now we're going to talk about cellular radio, a quick overview of that, and then planning, site planning setups and cell layouts and things like that, and then we'll delve into the channel model. So it was in the 1970s that mobile radio came into being. It was originally called the Advanced Mobile Phone System, or AMPS. I didn't grow up in New York City. Joseph, you did. I think there were phones, mobile phones existed in cars before AMPS came along. It was done by some other means, though. I really don't know what it was, but I think there was.
My family didn't have them, so I'm not saying it didn't exist, but
yeah.
I never saw them.
Yeah, this is back in the 70s, though. So.
I also didn't exist back then.
Yeah, so you wouldn't know, but I was growing up then, so that's when I was growing up in the 70s, and what I was going to say is that having two-way radio and other things was something that was common. I mean, delivery trucks would have a two-way radio set up, just narrowband FM that you'd be a two-way radio system would have an assigned FM, narrowband FM carrier, and they could use that, like taxis would have that. So they could call the taxi drivers from the dispatcher and say, go to this address, pick up some customers. That makes sense, doesn't it? I mean, they had to do that. So then things moved along, and that was having autonomous phone call making capability is what the AMP system was all about. It used analog FM. Spacing was 33 kilohertz. There was no data on it. It was just voice. And that was a big innovation. The phone was about the size of a small brick. You hear people talk about the brick-sized cell phone. So my father, being a gadget person and an amateur radio person, he had one of those phones because he had to have the newest technology if he could afford it, and he always managed to afford it because he was just one of those types. I mean, I like gadgets too, and I think engineers tend to like things like that, if you can afford them. I mean, some things are just way too expensive. So that was first generation. Then in the 90s, things progressed dramatically with second generation, with the standards now being digital transmission. I guess I'm skipping over what was in between there, but in between there, people longed for data over their AMPS cell phone. So something I worked on, probably was in, I don't think it was in the 80s. It was much later I worked on it, but there was a standard called CDPD, Cellular Data Personal Device. I don't remember what the PD, Cellular Data, CDPD. I worked on CDPD, which was, and I have some papers that I did with a graduate student. CDPD was for the AMP system, and then what was going on, they were using GMSK. So GMSK was used as the data link that people were allowed to start doing on their first generation cell phones. They could do digital data with CDPD. And I did a paper, like I said, with this student, and we were looking at interference, and that's the next topic in this area, is looking at cell reuse in a cellular system, and how I was looking at interference of GMSK from analog customers that might be in adjacent cells, or not adjacent cells, but in the reuse pattern. So we were looking at interference, and that was fun. That engineer is currently working at Kratos, the guy that did that for his master's project, master's thesis. So second generation came along, and Europe had GSM, which we've already talked about. Frequency division multiple access is how GSM worked. So you were assigned different carriers, but actually there is a TDMA aspect to GSM as well. But the US and Japan adopted a strictly time division multiple access scheme where you would have a carrier assigned, and then you would share that carrier amongst many users in the time division multiple access, and that require accurate timing. But actually, as I think back on it, I believe both of these systems had aspects of the other. FDMA had TDMA embedded in it, and TDMA had FDMA embedded in it, only because a TDMA carrier at a cell site would have, I'm trying to remember how many carrier frequencies you would have, but you'd have multiple carrier frequencies, and each carrier frequency had time division multiple access. So frequency division multiple access doesn't have the same critical timing needs. It's just you're on this channel, I'm on this other channel, we're not going to mess up each other. But TDMA brought in the needs to have very accurate timing, because your handset would have to know this is your slice, and then there'd be 6 others or 5 other slices to other users, and then you would get another slice, and your speech vocoder would, get another bunch of samples, and then it could put your speech out. And that was 2 of the 3 standards in 2G, and then later we got IS-95, and IS is interim standard, is what it means, whereas the standard that US and Japan used for TDMA was called IS-136, which I worked on that too. That had a QPSK scheme, but it was, I'm trying to remember what the name of it was. I think it might still be mentioned in the book, but was a scheme that was 4 points, and then the next symbol it would rotate, and then it would rotate back again. So it was, I'm trying to remember what the name for that is. Has anybody ever read about the name of that modulation? I studied that a lot, that modulation scheme, and it was done for efficiency reasons again. Now it's bugging me that I can't think of the name of it. Differential offset QPSK. Yeah, I think that was a DQPSK. Differential offset QPSK was the name of it. It totally went away when we moved off of off of TG. And then, of course, IS-95 was the standard Qualcomm pioneered for code division multiple access. As we rounded the mark to end the second generation era, eventually the United States and Japan threw in the towel on their IS-136 TDMA standard, and they just adopted GSM. So we were down to 2 camps at that point. We had GSM in the US and around the world, and then we had the CDMA type. So who were they? Just thinking back in time, everything kind of coalesced. From the TDMA camp, there was a bunch of companies like Southern Bell or Southwest Bell. There was AT&T, and then a few other different providers around the country, and they coalesced into ultimately AT&T. Makes sense, right? They became really, really big. And then over on the CDMA side, we had Verizon and T-Mobile and Sprint. So those 3 were pretty much working in the CDMA domain, and Verizon gobbled up some other smaller companies that were doing CDMA, and so they grew really big, and AT&T was already very, very big. And Sprint and T-Mobile kind of were hovering around, but they didn't really, I think T-Mobile might have done TDMA too, but they didn't really have a place they could call home, so then more recently they joined forces, but they're still distinct in the community, right? T-Mobile, Sprint is now one operator, AT&T is an operator, and of course Verizon is a national operator. And that's where we're at right now, I believe, right? And the other small companies that are out there are generally just buying their network access from the big 3. And I think, I don't know, has anybody ever taken interest in this? Who's the biggest and who has the most coverage? They certainly tell you, why you want to go with them, but
I notice, like, in different parts of the country, Verizon or AT&T are better.
right.
It's not one of them is better everywhere.
That's absolutely right. I don't have very good coverage. I have AT&T. Why do I have AT&T? Well, when my sons went off to college, that's when we had to get cell phones for them. My wife and I didn't have any cell phone up until they went to college, which was in 2010, is when my sons went to school. And I was way behind the scenes, but I didn't want a cell phone. My wife didn't want one. We just had this pact. We didn't need one. But then when our sons got one, then I got an iPhone. And my wife was working for FedEx at the time, and FedEx had a really good employee discount through AT&T, a really, really good discount. So that's how we got started with AT&T, because of the discount that her employer offered. a little bit of history there, but you know, across my family, I think my family is very we're either Verizon or AT&T in my siblings, and I have 3 other siblings, so I think we're about split 50-50 actually between the 4 of us. What do you guys use? I'm just curious.
I've been using the off-brand ones, like I have Metro PCS now.
Okay, but that buys its services on somebody's network,
Yeah,
right?
I don't know.
You don't even know what network it is, though.
No. But I think the point is, right, they're cheaper, but then they don't buy you new phones. That's like their selling point, right?
Right.
So like Verizon and AT&T have more expensive plans, but they'll sometimes upgrade your phone for you.
Or yeah, we do the family plan. I mean, even though my sons are pretty independent, I mean, one still lives at home. My wife and I decided we're just buying phones for our 2 sons. We won't do that forever. Hopefully someday they'll flip that around and they'll buy us phones, but I mean, buy us our service. But the family plans make it fairly good, but that's a continual shuffling, right? That's the marketing strategy.
Yeah.
It's always on the move, trying to get people. Or when I worked for Paracle Communications that did cellular stuff, and I worked on some Sprint projects, and I don't remember what we were doing for Sprint, but I know I worked on a Sprint project with that company. The founder of Paracle called it churn. The word is CHURN. So the churning factor is jump ship, go to another provider, come back, go to another one. So
I had Sprint for a bit, and I found it was good on the East Coast, and it was pretty much awful everywhere except for the East Coast. I don't know if other people had that experience, but
well, see, now we have T-Mobile though, so T-Mobile
yeah, it might
is
be
Sprint.
better.
I don't really know though. I know that Sprint did not have a very dense network when I worked on this project with them many years ago. They were just barely getting started. I think
They were cheap and good on the East Coast, but if you had to go fly anywhere, your phone was basically useless.
yeah, I don't think AT&T is as good as they say it is though. I find it to be not very good coverage. Like in my house, it's not very good really at all. I have 1 bar typically, but okay. So then we went into 3rd generation, and things were simpler in 3G because we only had GSM and CDMA. So network capacities improved, data services got better, and we were striving to get higher data rates. And during this interval from 2 to 3, people were turning from voice to data. I mean, data ended up being the driving factor. I think we all know that today, that you don't really pay anything extra for voice minutes. Originally, you paid for voice minutes, and you got so many voice minutes and so much data pull through the network. But now, I don't think we pay, they don't break out the voice minutes at all anymore, do they?
No.
And that's I guess, I know I'm rambling on this topic a lot, but I think it's just to understand it. It started with all voice, and it kind of got 50-50 around 3G, and then in 3G time frame, it just definitely crossed the line to data. And then as 4G was rolling out, it was already data. You don't pay for voice anymore. It's the data pull that you pay for, and the program that I have with my family is so much data, and AT&T has the program where you get to roll your data from month to month. I mean, you can't roll. It's not a moving average, or it's not an accumulation, but you get to roll the previous month into the next month, and then so on. We have just so much data, you don't even use it. I mean, I don't stream things, but my sons might stream things. My one son, who lives by himself, he streams a lot of content because he doesn't watch TV, so he gets to stream Comcast and other things, just because we share that account with him too. It's interesting though how it's changed. I can't use the data though. Maybe with 5G they'll restructure it so that you're going to run out of data and you're going to have to spend even more money with the data plan, something like that. All of us are different though, right? We all use that capability differently. So 4th generation with the LTE replaced the CDMA and the time division, frequency division, GSM, which was based on GMSK, and then for a while in 3G there was also EDGE, and EDGE was a GSM thing. EDGE stands for Enhanced Data Rate for Global Evolution or something like that. I mean, I worked on EDGE for a little bit too. EDGE is actually an 8 PSK system, or was an 8 PSK system. And if I drive due east of here on Highway 94, which eventually gets on Highway 40, goes through Oakley, Kansas, and then joins on to I-70, I will, in the small communities in the eastern part of Colorado, you'll see a lot of cells there that still run EDGE. So it'll light up on my AT&T phone saying it's an EDGE site. And that had enhanced data rate through an 8 PSK scheme that was devised by the GSM community. So there is 8 PSK out there still, and it was to get higher throughputs. It was meager though because the bandwidths were not that great. So as we move now from 4G and are trying to get into 5G, I'm finding that things are not as quickly as I expected them to be. But there's so much more complexity in 5G, and then people are already, of course, working on 6G, that it's going to take a while, and it has to be done in a financially sound way. I don't know what that means exactly, but I think the big providers kind of bully each other around because no one wants to spend more money unless they have money they're generating from their customers. But service expectations force them to spend money to upgrade their networks. One of the things that's always been around since 2G is backward compatibility, so handsets are still complex. I mean, my handset, which does 5G using the Qualcomm chipset that I got last December, bought 3 iPhones for my wife had broken her phone, so she had a relatively new one. She bought a used one, but then I just went out a year ago and bought 3 iPhones. iPhone 12 is that, or 10? I don't know. I can't keep up with the numbers, but so that had the new chipset. But I can be in an EDGE site, so I still have that 8 PSK GSM backwards compatibility. So that adds to the complexity. And this bullet here, I rewrote some of this just actually this morning. It was very significant as we moved from 3G into 4G and now into 6G or 5G that Sprint and Verizon, the champions of CDMA, totally put that in the trash can, and they don't use it at all anymore. To me, it was a big deal because it was such a heavy push that they were making when they were launching all of that. So now we're going to take a break, and we'll come back and look at this thing, which is going to get us into it. There's only one homework problem, but there is one homework problem on the cellular topology stuff. So I'm going to stop this or pause it. Resuming the recording. Let's just look at cellular design foundation. So we have cells, and we have the concept of a reuse pattern. And then associated with that is the reuse distance. When IS-95 was the going thing, it was a one-cell reuse pattern, but the most popular reuse pattern is 7-cell reuse pattern. but we're going to look at geometries that adapt, are tunable for different reuse patterns. The idea of the reuse pattern is to allow the same frequency bands to be used over and over again in the geometry of the cellular network. And the consideration in the reuse pattern is how far away is another cell that's using the same frequencies that you're on, because if I'm talking to the base station and then the cell that's reusing the same frequencies is that far away, it can cast interference into my cell. And that's stuff that I did over the years with different students and things, is the interference problem. And it's designed to minimize interference, of course, and one of the factors that thwarts, I think, Colorado Springs maybe more than some other metro areas is the fact we do have elevation shifts. So elevation means that things can propagate further, and one of the things cell sites had to do over the years is control the height of the antennas. You know, you would think an antenna should be really tall so that I can serve this cell that's right around. If I'm the tower, I want to serve my customers in my cell, but when your antenna is really tall, then it can also propagate further and reach over to that cell that's reusing the same frequency. So if you drive along the interstate, like I-70, which I've driven along a lot when my son was living in Kansas, you'll see these big tall cell towers, but then you look at them, and if you notice, or I'll ask you, have you noticed that the antennas are not at the top anymore typically? Have you ever noticed that out in a rural area?
I haven't paid attention.
Okay. I pay attention to that stuff just because I'm curious. But so a lot of what happened as the cell densities grew and the cells got smaller, the towers that were big and tall, they didn't tear them down, they just simply mounted the antennas lower so they can serve the smaller cell, and then the reuse pattern can be supported. So that's what we're going to be looking at right now. The center of each cell is a tower and associated base station. The base station connects to a mobile switching center. This was the terminology. This acronym may not be appropriate anymore, but this was in the beginning, MSC. And then the MSC would connect to the public switch telephone network to allow data voice traffic to flow into the PSTN, but now it also has to connect to the internet, obviously, because that's where most of the data flows, through the internet backbone, which would be the fiber optic part of the network. I know it's hard for you because of your ages to think PSTN, who cares about that? But my father, you know, who's been deceased for about 2.5 or 3.5 years now, he mostly used his phones for talking. He got into texting and messaging and email, but he still loved his phone for just talking. I mean, that's how he communicated with his friends, and it was always voice. I almost never use my phone for voice. I mean, when I have to, but I just don't use it that way. And I'm sure most of you are, you use voice far less than you do data. I mean, maybe, I don't know, 1 call a day or less for me. Most of it's just data. So thinking of the backhaul out of the base station being into the PSTN seems old-fashioned because the fiber is there to take all the data into the internet. So here's a layout of a cellular network, and this is just emphasizing the 7-cell reuse pattern, and I'm going to explain how that reuse pattern gets established, but these are some of the attributes of the reuse pattern. The shaded one is the one of emphasis, and it's just showing that wherever you see the 1 appear, those are all of the cells that are pushed around that you'd worry about interference from, but you have the nearest neighbors are the ones that you would be mostly concerned with, like. And then there'd be one from over there. I mean, the ones that are two reuse patterns away would be much less concern as the ones that are your nearest reuse neighbors.
I assume you'd have to use pretty directional antennas.
No, we don't. That's the whole thing. It's an omnidirectional because that's the nature. You want to be able to be in your cell and you want to be able to talk to the tower with your omni, and you don't want to, you know, as you move around like this, you know, what do you do when you talk on the phone? You don't stand still, you move around. Now, the towers have a pattern though. They don't want to have the panel antennas, which are those vertical panels that you see on the cell towers. You don't want to have those, so that is an antenna array. You don't want to have it of elements, so it wants to spray its energy down a certain amount. It doesn't want to go straight out because that would go interfere with another cell. You don't want to go up in the air really at all, although it does some. I mean, think about the 9/11 attacks that occurred in New York City and so on. People were on those planes and they were on their cell phones and they were able to talk to the cellular network. So the cellular network had enough reception capability. I mean, I'm just using that as a vivid example because we can think back to the recordings and everything that were captured from those events. And in general, though, we don't have our cell phones turned they're in airplane mode when we're in an airplane for the RF interference reason, but in an emergency, you can. The cell network is not totally dead above it, but it's designed to tilt down a certain amount to get the people kind of, you know, at the feet of the tower and then avoid the interference to the reused frequency bands. The MSC, Mobile Switching Center, I always forget what that stands for, has to coordinate handoff and handover as the user moves through the geometry. So all cell technologies have that. They have control channels that your cell phone listens to. Your cell phone is, that's the reason why it sucks down your battery in part, because it's always trying to know where you're at, even if you're not making a call. It's just doing that handoff, and it wants to know where you're at, and then it wants to know if you're moving, what's the next place you're going to go to, because it wants you to be seamless, provide a good quality of service. So that occupies things, and plus power control is wrapped up inside of that. Just a variety of things. Plus, yeah, your phone actually does need to hand off when you're driving in the car, because you get messages and everything's just alive like that, because that's the nature that we've now come to expect with our phones, right? I plug my phone into my car and my voice messages will get announced inside on the radio, and all those other things can happen if you let them happen. My car's kind of primitive. My wife's car is a little bit newer, so she's very adept at doing texting and listening to text while she's driving, because she has Apple CarPlay in her car. And Apple CarPlay, if you don't have an iPhone, you don't. I mean, it's probably something similar with the other types of phones, but to me, CarPlay is pretty nice because it's very similar to the phone itself. Only now it's in your car and your touch screen. It's safe and it does what you want it to do. And you can use Siri, the voice recognizer, to compose your text message if you want to do that, or emails, I guess, too. I've tried it. I mean, I have my watch and it talks to my phone and it alerts me, but I still have to do that when I'm driving, and I don't feel particularly safe except tapping it at a light and, you know, looking at the latest message or something like that. But handoff and handover, important. Radio wave propagation and transmit signal power level are factored inside of that. The next thing here is the hexagon shape is just convenient because it as it says there, tessellates over the plane. So the hexagons fit together perfectly, so we see we have coverage. It's just sort of a hypothetical thing now. Okay, in a geometry that's normalized, the cell vertex is at a radius of 1 over the square root of 3 if it's a hexagon. And this is the one homework problem I gave you, has to do with working through some of these geometry calculations. So if you mark the centers at coordinates u and v, let's say, of a particular cell, then you're interested in what is the distance in cells in a reuse pattern. So the way these hexagon geometries work out, n is equal to I squared plus I times j plus j squared. So the I and the j define the coordinate shift. So this is how it's set up for the 7-cell reuse pattern. I mean, the dark shaded ones are the reuse cells, but in general the coordinate shift is denoted by the integers going x and y that you see on, if you look at how the integers shift. Actually, it's not x and y, it's 2 and 1 takes you along the diagonal, this guy here, and then vertically, and this one is how the picture is showing you get from the center of one cell to the center of the next adjacent cell with 2 and 1. And the 1 over the square root of 3 is from the center to the vertex on the hexagon. So I think the homework problem, you play with this a little bit. CDMA, because of the nature of the code reuse and everything, they set that up to be a reuse factor of 1. So every cell was the same. They were just isolated by their code reuse, and the multiple access interference that we were looking at last week. The AMPS did n is equal to 7. GSM did n is equal to 12 in Europe, I guess. I'm pretty sure in the US it was always 7. If you're doing co-channel interference analysis, then this DCO, which is the distance for co-channel interference analysis, I didn't really point that out from before, but that would be that distance right there from the cell centers, and then you could go to the cell edge if you want to, but this is the cell center distance, and it's normalized by the reuse number n, and then r enters into that, which is the radial distance. So this is just a table that I think appears in the book for different I and j values, reuse numbers, and then normalized distance to repeat cells. So if you get into this co-channel interference analysis, which is what I did with some students and when I was working at this company, you can model the propagation loss. So this PR is actually not the received power, but it's effectively the loss, because it's showing between R0 and R is the radial distance between one user and another user in the same cell, or another cell tower, I guess. And K is the power in watts. Never mind, forget about that. K is the power in watts, but R over R0 is the ratio of the distances. And if you think back to field and wave theory for a spherical wave, the density or the power flux density drops off in an ideal spherical wave as 1 over r squared, right? But in a cellular environment or indoor environment, you have an exponent alpha, which is not 2, it's greater than 2 because things roll off faster. So here it just says 2.5 to 4. So this is the exponential factor. in attenuation. So I do have a note on that. It has to do with other things coming into play, scattering. If you express that in dB, then you get this formula. And if you want to go actually into the mobile environment, you might want to consider what is the interference power from the co-channel base station. So that would be this model right here, and then you're not interested in that actually DCO, but you have to subtract the position of the user, which is the green dot in this picture. The user is not sitting at the base station, but the user could actually be right at the edge of the cell, and that's where it's going to get closest to another base station. Or vice versa, is going upwards from that. But this model is thinking more in terms of what the user is doing with their handset, and are they going to get the nice signal they want from their local base station, or are they going to get a lot of interference from one of the co-channel base stations. So this is an expression for signal to interference ratio based on so much power and coming from each of the base stations, but in reality that's going to work itself out if we're just going after how many dB down the interfering cell is relative to the desired cell, and that's going to be the signal to interference ratio, and that's this bottom formula for 6 co-channel interferers that are going to surround the cell of interest. And I think these are what the numbers come out to be. It involves the geometry of the cell and then this factor 7.78 dB that it drops by, and then alpha is inside of that too. I'm not really giving you a lot of detail in here, but I remember when I worked for Paracle Communications, my boss at that company, his deal was when he was writing papers for conferences and things, he would assume that the user was uniformly distributed over that cell, and then he would move that user around so it would get closer or further away from certain cells that were interfering, and then he would get the average signal to interference ratio for all the geometry possibilities. Is that believable? And then you could pick a particular scenario, like the edge is where you're going to be doing the worst, and right near the base station is where we're going to be doing the best. And of course, when you're at the edge, you're teetering on the need to hand off, because as soon as you get a little bit weaker, then you're going to cross into an adjoining cell, and then you're going to be handed off. So that factors in there. I found it interesting. I haven't done any of this for a long time, but it's all part of what goes into modeling and understanding factors, and I'm guessing stuff you're doing with Dr. Semiari, you're doing some of these things, right? You're having adjacent channel interference, or maybe not. You do?
Yeah, we measure the interference from other cells and allocate powers to minimize that interference.
Right. So you've been studying this a lot then, probably.
Yeah.
Okay.
One of our,
And of course, a lot of what you do is kind of idealized. If you wanted to go to ray tracing models, which I know he has software for that, and that's what I got involved with too, was understanding what are some scenarios. But ray tracing is just a very specific geometry, and then you can have statistical models which give you sort of the ensemble average of what types of things you might expect, right? And then if you have buildings, well, we're going to get into that right now, but you have different scenarios, whether you have things I was doing a long time ago with the ETSI models, which is the European standard ES, what does ETSI stand for again? European Telecommunications Standards industry, or I don't remember what. Have you bumped into ETSI standard yet? ETSI? Okay, well, they had a set of propagation models, which we're going to go into right now. Not the models, but just the general stuff. They had dense, urban, like I think New York City would be an example of dense urban. Then they have suburban, light suburban, and then they have things like rolling hills. I mean, there's like, I think there's, at least 5 different variations for statistical propagation models that you could use if you're trying to assess the viability of one something or another over another something or another. So besides additive white Gaussian noise in the mobile radio channel, there's also fading. And the 2 types of fading that you deal with in the mobile radio channel are Doppler spreading, because it's absolutely the case that the mobile is moving. Even if the mobile is a person walking, you still have to consider that in your model as a walking user or a driving user. And that introduces Doppler spreading. That's the frequency shifts that you get, and that's going to be present. And then the multipath, which introduces the delay spread. And the delay spread is what we were looking at earlier for the OFDM and the cyclic prefix. And that introduces frequency selective fading. So this picture, when I was first getting into mobile radio and attended the IEEE Vehicular Technology Conference, which is where I went frequently, it's called the VTC, and it still exists to this day. I don't know, does Dr. Semiari like VTC, or does he like some other conference?
Yeah, one of our papers for VTC.
Okay, so I went to the VTC. He probably doesn't believe that I did that, but I went to the VTC always. I was always there with students and attending the sessions. I liked the VTC a lot. I only went in the U.S. I didn't go to. It would always go U.S. or Canada, and then it would go somewhere else in the world. So I was only going to it when it was here in this country, but I went to it very, very regularly and saw the same people usually every time I went. So one of the first things when I was getting on board with mobile radio stuff was this picture right here and understanding the fading channel model. So we've got delay spread, which is in the upper left there, and that's the impulse response. That's just showing it as a continuous excess delay. The picture we looked at earlier with the cyclic prefix just showed the spikes, right? But this is just showing it as a continuous. There's a high density of multipath, so it's enough that it's drawn out as a continuous plot. And then the dual function under the Doppler spreading, which is the motion of the mobile, creates this frequency shift. And a standard Doppler spread model under an ideal setting that was developed back in the 60s under the AMPS model. I have this old book, but it's been used a lot, though, is this horseshoe-shaped Doppler spread. And it just comes from a uniform distribution of rays about the mobile. So you've got signals arriving with Doppler on them, and some of the rays are going to arrive with an increased frequency, right, if it's coming at you. And if the ray is pulling away from you because of the way your motion is, a ray is at your backside and you're going that way, and the ray is bouncing off and coming at you, then that would be a decreased frequency. So the bottom line is that the Doppler spread tends to be symmetrical about the nominal carrier frequency. So you have a max and a min. And this is a distribution then, because it's saying you're immersed in an environment where you've got rays coming at you from all directions from the same source. So you get that Doppler spread due to your motion. Then when you go to the transform domain from the delay spread model, you get what's called the space frequency correlation function. And this is the Fourier transform of the impulse response. And then you talk about what is the width of that. I'm down in the lower left now. The space frequency correlation function you have the maximum excess delay up on top is tau m, and that factors into the width of the frequency space correlation function, which is 1 over the delay spread, and that width there is called the coherence bandwidth. So what it's saying is that the more delay spread you have, the wider the coherence bandwidth is going to be. So, or is it the opposite? No, it's the inverse of that. The coherence bandwidth is tiny when the delay spread is wide, saying the signal is, the coherence bandwidth is very narrow, so you can't support a very wide bandwidth signal because the coherence bandwidth is narrow. You need to have enough coherence bandwidth to support a wideband signal. Except for spread spectrum with the rate receiver, that gets around it another way. But then the Fourier transform of the Doppler spread leads to the time-space correlation function, and that's just giving you a measure then that's 1 over the RMS value of the Doppler spread, which is called the coherence time. So it's going from frequency to time, and if that goes from positive to negative in a short amount of time, that's telling you that it's not coherent for a very long time because it's in such chaos with the Doppler. So you'd have the space-time correlation. And for this idealized Doppler, that spectral shape has got the J0 Bessel function in it, and 2 pi times the nominal maximum Doppler frequency, FD, is in there. I don't know, I got into this stuff because every time I went to a VTC conference, people were always using these terminologies. They would either be using the top two or diagonal, or, so you have to just relate to all of them. And I bet you're seeing these in your models, right? These different views.
Yeah. In our model, we use a different numerology for OFDM and analyze the performance of system.
But you're either using coherence bandwidth or delay spread for one type, or Doppler's max or coherence time, I'm guessing. Yeah. Okay. So Doppler spreading details. Receivers moving relative to the transmitter, and all the reflecting surfaces contribute to the Doppler spreading. And so this is the scenario there. You've got a transmitter, you've got objects for waves to reflect off. Remember when we looked at Rayleigh, we had Rayleigh and Ricean, and Ricean was where we had a direct line of sight, and Rayleigh was where it was just all secondary paths like this. And this just shows you as the line of motion as you're traveling, each of those rays are changing in length as you move through the environment, and those contribute Doppler from a single ray. But then when you get all the rays compositing together, you get the Doppler spectrum. And this is just showing rays that are coming up from behind, but in general there would be rays coming from all directions, is what I've always seen in the paper models. But obviously that's what makes this so, I'll say, thrilling and frustrating, is the fact that the scenarios are many. I mean, you can't just say that you're always in an environment where the rays are uniformly distributed around the user. They might only be coming from certain directions, or I don't know. The thing that where I got interested in ray tracing is that you're sitting on the street and a big truck drives by, and there's rays that are going to bounce off that truck and are going to come right at you, so you're going to get a momentary burst of Doppler shifting going on just because of that moving vehicle relative to your slow walk. And I don't know, I'm trying to get you to think that it's not simple, it's complicated. The channel is very complex. We're trying to manage the channel and understanding its characteristics. So drilling in a little bit further, this is a single ray, and you've got a velocity, you've got the angle separating the traveling vehicle and, say, the base station. So there's a cosine of psi that shows up in this model. And ultimately, you end up with something that kind of looks like this as a function of time. You've got phase shift due to the fact that this is changing. You've got time delay over here due to the velocity. And then you've got Doppler. The Doppler is showing up because you've got a high frequency carrier, F naught. So when you pull out of that, you've got a Doppler frequency, which is going to be F naught times 1 minus V over C, or it could be plus or minus that. So you end up with Doppler shifts that are going to be plus and minus, depending upon whether it's arriving or retreating. And then you've got the angles of arrival, the cosine of phi. So I got really excited about this for a number of years because I was working on channel prediction, and I was trying to figure out how you could predict the channel so you could do adaptive rate changing, and I was trying to predict the changes. And I had a PhD student involved with writing. We were trying to write our own ray tracing model because we couldn't buy one because it cost too much money at that time. So we were curious about ray tracing models and angles of arrival and how I would manage that sort of in a theoretical model of the channel to do channel prediction. It's crazy stuff. I don't know what, I did it because somebody wanted it done. I mean, they were like, adaptive data rate works, but we have to know the channel. You have to estimate the channel. So I got really involved with channel estimation. And being that we're now at millimeter waves, I think it's even crazier because the frequencies are so high that things change a lot more rapidly because of the really high frequencies. So I think it's crazy. I mean, it's just really hard, right? If we don't want to communicate, we don't have to worry about this. But if people want to get, you know, their streaming whatever off a millimeter wave carrier, it's a lot more challenging. And that's stuff you're doing, I think, right? Trying to figure out how to make that work at millimeter wave frequencies. So these are just some numbers. Whenever I worked in this area, I was always curious about what the Dopplers were, and these types of numbers were always used in examples. If you're working at the two cellular bands at that time were the original cell band at 900 megahertz, and then the PCS band that was allocated at 1900 megahertz. But now we have a lot more bands allocated. I was mentioning the 5G band that the project I'm working on is from 3.3 to 4 gigahertz, but you could translate all of these numbers. So 10 kilometers is 6.2 miles an hour. The Doppler is pretty tiny there, 8 hertz and 17 hertz. You go all the way up to highway speed or a low highway speed of 62 miles an hour. The Europeans used kilometers per hour, so their numbers they liked were 10, 50, and 100. But you can just see how the Doppler is getting pretty large at the 1900. And if you're at, you know, go up another octave to 4 gigahertz, you know, from say 2 to 4, that would double that again. And then 8, it's going to double it again. And you go up all the way up to 33 gigahertz or whatever. It's just huge, the Doppler. It's getting really, really big at a highway speed. So I always tell, I don't tell you as students because you know this, but I always tell people that don't understand that just to listen to a radio or talk on a radio when you're driving on the freeway and dealing with all that Doppler spreading, it's amazing that it works at all. Have you ever thought about that? FM radio has been around for a very long time, and it works. You just turn it on. We're driving 75 miles an hour on the interstate up to Denver. You listen to the music. Sounds good, and you don't even think about how that signal is all wrapped up in a lot of Doppler on it. It gets shifted, and then we track it with the automatic frequency control in the receiver. And then data communications, of course, is more complicated because of all the coherency issues that we've talked about. So, what is going on? My watch is dinging, but it's Xfinity. It's my wife.
I was gonna say, I guess, yeah, for analog you'd use a PLL to track, because I don't hear the pitch of the radio shift when I...
Yeah, FM doesn't. Yeah, because of the way FM is, you don't hear the Doppler shift. Because down at a low frequency, it does the Doppler shift, and audio band is minimal. It's the carrier that the Doppler is big at because of the way the math works out here. F naught divided by C. So it's the carrier that sees that big Doppler. Down at baseband, it's hardly noticeable. It is a perceptual thing, though. You're right, and because I like playing with audio, I did build in my Pi Audio Helper. I was thinking of writing a paper this past summer because somebody had asked me to contribute. It was going to be an invited paper, and they said, take your paper from this other conference and do something new in it and add some more things to it. So I had this idea in my head, and I was going to create Doppler shifts in audio, and I built it up using that variable, that interpolator. Remember you talked about one day? I built it up with that, and I put something in motion. I put it in motion like a train or a car, and it would pass by me, and I would have the radio model in there, and it worked. I mean, listen to audio, and I hear it come up in frequency, and then it would drop in frequency, and it sound roughly constant. The activity is right when it's going past you where it's changing, and it came up in pitch and then went down in pitch. The music did whenever I was listening to. But the processing power was a lot just to do that little bit of simulation, but I know it could be done, and I still think about it, but I don't think about it that much. I think about it, would you go to the theater and would you really like that virtual reality effect that could be applied in a scene or something? I mean, if they do it right now, they record it, like an ambulance or something, and we hear the Doppler frequently on a TV show, right? You hear the ambulances, but we just have to walk outside and we hear that Doppler in our ears. But how do you put that all in a digital environment? That's what I was thinking about. How would that be cool? And I guess I'm not a gamer, so do games do that?
Yeah, I have no idea.
Yeah.
Maybe.
That's virtual reality related stuff. That's the audio side of the virtual reality. How detailed do you want to get in modeling the environment where you'd actually hear the Doppler? And I started down that path, and it's in a Jupyter notebook, and I just haven't. I'll get back to it maybe someday if I want to try to go that way with the audio part of it. So I think we're pretty much out of time. We're close to the end. Just more details on these models that would lead to the fading pattern. And then you would enter into a delay spread model. So when you get all the way done, you can build that up, delay spread and Doppler spread, into one channel simulator. And I did that, and I haven't maintained it, but the graduate students I had back in that era when I was using MATLAB, I had a standard doubly spread channel model simulator that they used in their theses work, dissertation work. I just haven't. I'd like to convert it to Python, but I kind of lost interest in it because I was doing other stuff. But it got started because when I worked for a company, we had to contribute a channel model simulator for a cellular testing environment under the IS-136 standard. He was a member of the consortium, and he took the assignment at one of the monthly meetings to say he would contribute the channel simulator. He handed that over to me, and I had a paper published on what I had built up originally using DSP, and we made that contribution so that they could test. It was a vocoder competition where they were testing vocoders under different channels models, and the competitors were entering their vocoders, speech vocoders, and then in order to test them, they all had to play through the same mobile radio channel with a Doppler and delay spread, and then see the impact on the speech quality so that people could rate the quality of the speech for the different vocoder technologies with the same channel model for all of them. And that makes sense too, right? We have to do apples to apples comparison. That was for IS 136. Interesting. I'm going to sign off.